So please.
Thank you for a kind introduction, Professor Yasta. Okay. It's already Friday, and it was a really amazing week for me. And I have to say, I really appreciate for you for being here and for inviting me to have presentation for this study. This study is a luminescence retrospective dosimetry. Dosimetry. I'm sorry. In small-scale radiological accident, which means application of technique to the real case accident. Let me show you the brief start. What is retrospective dosimetry? It can be defined as a set of technique. It's kind of toolbox to estimate the radiation dose received by individual from past exposures, such as accident. In this toolbox, we have several tools like clinical symptoms and physical dosimetry using EPL and TLSL, and biological dosimetry that can measure the radiation-induced signal from chromosome, as Susanna introduced on Wednesday, and computational dosimetry using Monte Carlo techniques, and internal dosimetry and other potential techniques are there in the box. And among these techniques, TLSL focuses on the personal items like chip card, mobile phones, or cheap electronics such as smartwatches and earbuds and laptops, and even cigar and glasses can be used for these techniques. And these techniques have advantages in terms of measurement time compared to the other measurement techniques. For example, when we receive the sample personal items and disassemble it and extract some material and measure the signal, it will only take less than 1 hour to estimate doses. And in terms of detection limit, is much less than the other techniques too. So due to these features, ICRU level 94 recommended this technique can be applied to the initial phase of radiological accident to the individuals. This is table of application of radiological dosimetry in historical accident cases. The accidents were selected arbitrarily from Chernobyl, Goiânia, and Fukushima, and Chilka. And among these accidents, biological dosimetry applied every individual accident. That means this technique is kind of golden standard in our field. And EPL was applied by using tooth enamel and bones, and sometimes it used the fingernail for the recent accident. And in case of TLSL, also used for the large accidents such as Chernobyl and Fukushima. But in these studies, they only focused on the such material like brick and ceramic that can be extracted from houses located the accident site. So today's presentation is aimed to report the use of luminescence technique applied to personal belongings in real accidents occurred in South Korea between 2016 and 2024. So we want to assess the potential of the technique in small-scale accidents, and we discuss about the consideration on regulatory and technical perspectives. For this study, 3 institutes were involved. HINS, Korea Institute of Nuclear Safety, in charge of regulation activity, and sometimes they investigate accidents and they determine the final doses. And CARI, my institute, is cover research activities and TLSL measurement and report doses for the TLSL measurement. And Brothers Working Group 10 is well-known international corporations. They provide technical support like training and some programs for the dose estimation. And they they held ILC activities, interlaboratory comparison activities. In terms of regulation and dose evaluation procedure is done by KINS. KINS investigate radiation exposure accident in South Korea, known by suspected cases or those limit exceedance reported by quarterly. And in this investigation, it covered documentary review, site inspection, and interviews to the victims. And it also applied retrospective dosimetry. That means retrospective dosimetry method include TLOSL are integrated into the regulatory framework in KINS. This table shows the data sources considered for dose assessment. We have multidisciplinary expert committee, more than 20 people consist of dosimetric expert and industrial representative and medical doctors to determine the final dosage using this table. In this table, we use primary individual monitoring data of those dosimeters, and sometimes we use secondary individual monitoring like EPD or ADR, and sometimes we apply DCA, TLOSL, EPR, and etc., and including clinical symptoms. They also review the co-workers' dose record, and sometimes they do the workplace-based dose reconstruction. That means numerical and experimental dose reconstruction, incorporating exposure geometry and interviews from the victims. And they also review the personal exposure history. So these tables are also provided by KINS. These application of frequency of retrospective dosimetry technique for the past decade. Among the techniques, DCA was most frequently used, more than 140 times. And in terms of TLOSL technique, it's applied for 11 times. It's small, but it has been applied once per year, roughly. And this table shows the field where retrospective dosimetry applied. That means the field where the accident most occurred. And among these different fields, NDT, non-destructive testing field, has many accidents, around 80% of all the accidents for the past decade. When accident was recognized by KINS, they sent investigator to the company. They interview with employer and exposed individuals. And they check the personal dose, of course, but they also confirmed that personal belongings were carried during the exposure. And they tried to negotiate them to donate the items. And in most cases, it was consented by employer and exposed victims, because it depends on the penalty of the regulatory things. And in this case, employer should buy a new mobile phone to the individuals, exposed individuals. So it was much easier to have a mobile phone compared to the large-scale radiological accident, even though it was not happened. And when the mobile phone was transferred to the laboratory, we disassembled, extract the mobile phone in the lab without any heat treatment. And sometimes we apply cleaning, etching using chemicals, and we prepare the samples like this is register and this is glasses. And we measure the TLOSL signal, and after we correct fading or background, any other correction, then we can report the reconstructed doses. The applied protocol, we only apply 3 different protocols: register OSL with PRIT, register TL with PRIT, display glasses with pre-bleached TL. Depending on the literature, the MDD, minimal detectable dose, is ranged around 30 milligray for register OSL, and 70 milligray of the 70 milligray for register TL, and 90 milligray for the display glasses. Even though register OSL shows minimum MDDs, lower MDDs, it its signal is fade faster than the other protocol. For example, the remaining signal after 3 months is only around 30%. On the other hand, the display glass shows 95% for the 3 months. And after applying these characteristics as a correction factor, we can get the corrected dose. And this shows a dose recovery test from the previously reported literatures. You can see the register TL and OSL protocol shows very nice result compared to the reference doses. And in this case, this is glass TL protocol, and this chip protocol, we apply this one and shows very nice result for even though it's relatively low doses in terms of extent. And of course, there is the other protocols and materials we can use and already published, already studied. And we thought these three protocols have a minimum reliability. That means it has reproducibility depending on the labs and depending on the time. So from these ILC activities for the past decade, and in these activities, mostly hosted by Eurados and IAEA, RANEP, and sometimes PREDOS, Korea Retrospective Dosimetry Group, they hosted the ILC activities. Sometimes it was blind test using known doses of standard irradiation, and sometimes it was field test simulating realistic accident scenarios. I will show you some of them. This was done in 2014. It's called Kato ILC field test. It was held in Austria. This exercise simulate benchmarked Cochabamba incident happened in 2002. To do that, they use these buses and put the iridium sources in the compartment of bus. And place the physical phantom on the seat and place the mobile phone or other personal belongings around the phantoms and measure the signal and compare the reference doses. Doses measured by the dosimeters attached on the mobile phone. This shows this is glass protocol and this is register protocol. It shows us some linear relationship between reference dose to the protocol we developed. I'm sorry. Yeah, this is the next exercise, which was held in 2019 in Sweden. The scenario of this accident, actually, I have opportunity to participate in this exercise here. And the scenario of this accident was multi-structural exposure in public area. So we placed 4 physical phantoms on the sheet and placed the sources on the center, and we made 4 different exposure configurations. And we also applied some personal belongings around the phantom, and we put the blood sample around them. And you can see the related result in these publications, but regarding phone dosimetry is in preparation, so soon it will be submitted. PREDOS, we also applied this we also try to have this kind of exercise to verify the reliability of technique we have. So the scenario we had in this accident, virtual accident, was exposure accident in NDT, non-destructive testing workplace. And in this experiment, we found we placed several mobile phones around the 2 physical phantoms, and we can compare the reference doses measured by TLD, and it shows some nice trend depending on the position and geometries. Yeah, finally, these pages. This is statistics on the use of luminescence technique, which was done from 2016 to 2024. For the in total 11 accident cases, we disassembled more than 20 mobile phones from LG and from Samsung. Sometimes it's from Apple. Where is it? Yeah, you can find Apple here. Then sometimes we apply the EPD, electronic personal dosimeters. Of course, electronic personal dosimeter record the dose itself, but sometimes there is some workers who turned off their devices and doing work. So in this case, we can use these devices. In terms of protocol, except case one, most of the mobile phones was only one protocol was applied for the individual mobile phones. I will tell you about this later. And in terms of time-seized radiation, because this accident was mostly recognized by the quarterly reported personal dose record, so it's very from 1 to 3 months. Sometimes it's more than 4 months. So we have large gap between the fadings. So we need to consider this as an uncertainty to estimate the TR-Russell doses. And this column shows TR-Russell doses, and this, for comparison, I included the DCA doses. And if you can see the green values, it shows matched. I mean the consistent data in terms of sometimes they overlap the uncertainties and yeah, they match it. And in some cases, the marked by red colors, this data shows significant differences between DCA and TR-Russell. I will briefly show these case studies. For the case 3, this one, which was occurred in 2017, overexposure was recognized by quarterly reported personal dose of around 120 millisievert at an NDT workplace using iridium source in chemical plant under construction in these places. In this NDT workplace, they use this kind of instrument. And this is source holders, and one workers place this cable end to the targeted position, and the other workers rotate the wheel here on the left side. Then the source is coming out from this container to the target position. Of course, if one takes a picture for the gammography, then of course the workers on the right side should avoid, or at least he needs some shielding. But in this investigations from Kins was found severe violations in terms of radiological protection was not properly educated. That means dosimeter was barely worn, and the environmental was poor. Working environment was poor, so shielding was not used. And even worse, worker occasionally stayed less than 30 centimeters from the bare source. I can believe this one, but it was happened. So as a result, high and homogeneous whole body exposure was expected from multiple tests. So from the clinical test, we found pancytopenia and aplastic anemia, which means it's more than 0.5 gray. And in additional investigations regarding health screening of the other workers shows potential exposures of 9 workers. This is dose assessment for the 9 workers. The personal dosimeter record was really unreliable. And for blood test, worker 1 showed significant symptoms, and worker 2 and 4 shows less significant symptoms. And for the DCA was around 1 gray for worker 1 and 0.67 gray for worker 2. And the other worker shows DCA values close to the MDD. And for the tooth enamel, it shows more than 1 gray. And in numerical reconstruction, it was around 1 gray too. However, TR-Russell using mobile phone shows 11 gray, 10 times higher. And for worker 2 is around 3 gray. We found this significant discrepancy in those, but we noticed that the worker interviewed that they had occasionally place their mobile phone close to the source, I mean the bare source. So as a conclusion, mobile phone dose may not reflect whole body dose, but it shows those proportional trend when we consider the biological and clinical evidence. And in terms of technical aspect, we disassembled 9 mobile phones, and we can find usable display glasses because some mobile phone uses flexible displays which don't have a glass, and some mobile phone has category B glass. This category B glass exhibit red emission, and it was not comparable to the privileged TL protocol, which only uses blue emission of glasses. So we couldn't use these glasses. Instead, we applied registered TL because the fading was quite progress. So we want to have more signal for the fading, and fortunately we get about 3 curves per mobile phones, and standard deviation between the sample was ranged from 7 to 25%. This is second accident, which was happened last year. It was quite amazing news in South Korea. And in this incident, suspected overexposure was reported involving 2 workers during maintenance of X-ray instrument used for vapor inspection. In the investigation by Kins, the worker encountered a malfunction of the system, and they decide to inspect inside of the instrument while the device powered on, because they believe the X-ray was turned off due to the interrupt, which was malfunctioning at the time. And the instrument was not subjected to personal monitoring, so there was no those values. And both workers conducted 15 minutes of manual inspection, including one of them uses their mobile phone to take photos. And in the clinical symptom, they found finger edema, maceration, vascular damages, like that. And those assessment, worker A interviewed that he positioned his hand around 5 centimeters from the source. From this is source, the source goes like this, and for 1 and 2 seconds. Worker B positioned his hand around 10 centimeters for 5 seconds, and worker B uses mobile phone around 40 centimeters for 10 seconds. So clinical symptoms show significant symptoms, and interestingly, we couldn't find any DCA values, and we couldn't apply EPL for the fingernail because it was too short to have samples. So as a result, TLOSL was the only available measurement for worker B using mobile phone. It was around 0.5 gray. And it was significantly different from the skin dose estimate by reconstruction of experiment. And it was quite severe in this reconstruction. It was around 70 to 100 to 20 sievert for worker 1 and 26 to 70, sievert for worker 2. And technical aspect, no usable display glass was found because the mobile phone has flexible display. And so we applied OSL, as OSL because the time of irradiation was quite short. And the problem was it was X-ray irradiation. So it was assumed the average energy of X-ray was around 20 kilovolt. So we have 2 considerations. One is potential overestimation. The other is potential underestimation. Register have higher responses at lower energy. It gives overestimation. And in cases, glasses and aluminum housing could attenuate the beam. So we decide to correct this by doing experiment using the low energy X-ray beams, beams. So we have to carefully reassemble the phone and use the same registers irradiated to 1 gray after this energy correction, we can calibrate the better source of the reader. So the dose was reduced to 38 milligram, 38 milligram, and the corrected dose was provided for the supplementary data to Kings. And this is the regulatory perspective. Personal belongings cannot fully substitute for whole body dose estimate from the experience. However, they provide minimum accessible doses in cases no dosimeter runs, usage is uncertain, lost or damaged, unreliably low readings, need for cross-validation, a suspected localized exposure was found, and exposure scenario was unclear. In this case, we can apply. And the method can support for triage. For example, it offers quick and preliminary data when biological dosimetry is resource intensive and could help prioritize further assessment, as we saw the case 3. And in terms of dose limit, to assess annual dose, effective dose is quite challenging, but more feasible to assess the annual skin dose limit in terms of detection limit. And in terms of practicality, increasing mobile phone usage at workplace indicate higher chances of applying techniques. And in small-scale accident, mobile phone donation is more likely driven by regulatory such as penalties or health concerns. And this is useful tool for targeted regulatory inspections. And in terms of technical perspective, we have to still investigate new material because the registers is reduced, and sometimes we don't have glasses. Validation of existing method is required for the recent mobile phone. And sometimes we need those conversion technique. That means those conversion from target material to the whole body dose can be very useful when we know the exposure scenario very well. For this, we have very nice tool like Monte Carlo or AI-based those prediction model. And we should consider the standardized method for the handling of outlier needed for when we measure multiple samples. This was not observed, significantly observed in this study, but it can be happen. And ongoing effort in terms of standardization and collaboration are still essential. To conclude, I will skip this one, but this, I have to say, this is the first application of the technique to the real-world radiological accident, and the result highlight is potential for integration into emergency response and regulatory framework. Thank you very much.
Thank you, Hyoungtaek, for the very informative talk. So let's have a question and answer. Are there any questions or comments about Hyoungtaek's talk? Oh, please, Edward.
Yeah, very nice overview of the application and the very interesting real case application. So thank you very much.
Thank you.
My question is more related to preparedness, because you need an expertise to be able to respond when something happens. And to keep this expertise, we need funding in between this. And I think this has been a real challenge for many laboratories to keep funding a consistent program over the years so that people are trained and ready to respond. How do you see this? Is that easier in South Korea? How is the situation?
Yeah, it's really, really good comment. And we also consider the kind of things. And in these days, the fund is really limited in South Korea, and we have not enough funding for the training or continuing some activities like ILCs. But it depends on government, I think, and it should be continued. Yeah.
Okay, thank you. So any other comments or questions? No? If not, because time is up, so let's move on. So thank you, Hyoungtaek.